Welcome to my YouTube channel. Let's solve the third problem. The third problem is searching in rotated sorted arrays. Let's quickly read the problem statement. Imagine you have an array that was sorted initially, but someone rotated it an unknown index. The resulting array is a rotated sorted array. The challenge is to find a specific element in this rotated sorted array without reverting into linear search, right? And one note that they have given, every array element is distinct. So let's take an example. Let's say there is an array and the elements are present in the array. The array was initially sorted, but it is rotated to a particular index or an unknown index, right? Now what the challenge is? Now the challenge is the value k is given. You have to search whether this k is present in the array or not, right? So first value k is 10. So if is 10 present in the array? Yes, the 10 is present in the array. So what we will do? We will return the index of that array. So the answer is 6. Now the second k is 70. Is the 70 present in the array? Yes, 70 is present in the array. So we will return the index, right? The third is k is equal to 95. Is the 95 present in the array? No, the 95 is not present in the array. So if the 95 value is not present in the array, we will return -1, right? So this is the problem statement. I hope you understood the problem statement. Now what can be the brute force approach to solve this problem? A simple brute force approach is linear search, right? We will traverse the array starting from the initial index to the final index, starting from initial index 0 to final index n, and we will search whether the value of k is present in the array or not. If it is present, then we will return the index of that element. If it is not present, then we will return -1, right? So what can be the worst case time complexity? At the worst case is the value of k might be present at the last value, that is at the nth index. So the worst case time complexity for linear search is order of n, and space complexity we are using constant space, so order of 1, right? So this is a brute force. Can there be an optimized approach to this problem? So as this is a searching problem, so one searching algorithm that we know is binary search, right? So can we apply binary search in this problem? That is the question, right? So where can we apply binary search? We can apply binary search if on the basis of the condition we can split the search space into two parts. So if we can split the search space into two parts, then we can apply binary search, right? So for binary search, the two things we need a target. So here we have a target which is k that we want to search, and we need a search space. So what can be the search space for this this array? The search space is the rotated sorted array that is given to us from 0 to n-1, right? So this is the rotated sorted array, right? Now let's do some observation, right? Let's say there is an array, right? Index is 0, first value is 0, final value is n-1. Let's say the middle element is here, right? Now what are the possibilities or what are the cases where the rotation point can happen? Rotation point is the point from which the array is rotated. So there can be two possibilities. Either the rotation point can be in between 0 to mid, or the rotation point can be between mid to n-1, right? So let me draw it, what I am saying. So there can be two cases. Case 1 will be the same 0 to n-1, and this is the mid. So rotation point can be in between mid to n-1, right? So this is the rotation point at which our array was rotated. That can be case 1. What can be case 2? Case 2 will be our rotation point will lie between here, which is in between 0 to mid, right? So there can be two cases. First case is our rotation point lies between mid to n minus 1. Second case is our rotation point lies between 0 to mid, right? So let's solve some, let's do some more observation by seeing an example. So let's see the example for case 1. In case 1, let's check our original array that was given to us, which was 40, 50, 60, 70, 80, 90, 10, 20 and 25. This was the array given. Let me do some indexing as well. 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the lower index, this is the higher index, and to find the mid we know that formula is low plus high by 2, right? So from this case 1, at what point this array is rotated? So here we can see that this is the point at which the array is rotated, right? So this is the case 1 where the rotation point lies between mid to high. And can you see on one more observation? Let's take 2. Let's say whether the element which is present from low to mid is the element, all the element which is present in between low to mid, is the element is sorted? Yes, the element is sorted because low is 50, 40, 50, 60, 70, 80. This element is sorted. Is the element sorted from mid to high? No, the element is not sorted because 80, 90, then 10, 20, 30, right? So the observation that we can see from case 1 is that array is sorted from low to high or low to mid, right? Element is sorted from low to mid. This is one example, right? Another possibility might be that array is sorted in other case, right? But what observation that we are getting is one part of the array is sorted, right? Now similarly case 2, let me give the example for case 2 as well. Let's take an array 80, 90, 100, 10, 20, 30, 40, 50, 60, 70. Let me quickly write the index as well. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the low pointer, this is the high pointer, and middle will be here, right? So for this array, what is the rotation point? We can see the rotation point is at this point our array was rotated, right? If the array is rotated, so this is the rotation point, right? So this is our case 2, right? Now can you do the same observation that we have done for the case 1, whether the element is sorted from low to mid? Can you see the element is sorted from low to mid? 80, 90, 100, 10, 20. No, the element is not sorted from low to mid. Is the element sorted from mid to high? 20, 30, 40, 50, 60, 70. Yes, the element is sorted, right? So another observation that we can write from case 2 is that for this example, the array is sorted from mid to high, right? So in both of the cases, array is sorted at least one point, right? So let me quickly write what we have understood from seeing all the cases. So in every rotated sorted array, at least one part will be sorted. We don't know which part is sorted, but at least we know that the one part will be sorted, right? Either from low to mid or from mid to high, one part is sorted, right? So what we have to do, we have to check for k, right? We have to check if k lies in this sorted region or not, right? What that is we want to search, right? If the k lies in the sorted region or not, that is a question that we have to do, right? So if it lies, then what action we will do? We will move towards that sorted region, right? We will move towards that sorted region. Otherwise we will move in opposite direction. Right. So let's do the dry run. This is the observation that we get from this case 1 and case 2. Now let me do some dry run, right? Then we'll understand it more clearly. Let's take this previous array example. Let's say the array is a given array 40, 50, 60, 70, 80, 90, 10, 20, 25. This was the array. Let me do the indexing 0, 1, 2, 3, 4, 5, 6, 7, 8. This is our low pointer. This is our high pointer. Let me also draw the table that we always draw for better understanding and for better dry running the code. Sorted and action. Low, high, mid, sorted reason. Okay. So the low value is 0, high value is 8. So 0 plus 8 by 2 is nothing but 4. So this is our mid element, mid one, right? So can you make an observation whether the element in between low to mid one is the element sorted? 40, 50, 60, 70, 80, yes. Is the element from mid one to high sorted? 80, 90, 10, 20, 25. So no. So from index 0 to index 4, that is from low to mid, the element is sorted, right? So what we'll do, and which element we want to search, that we have not specified, right? Let's say the element that we wanted to search is 20. So for this array we want to search k is equal to 20. Now the next question that we have to ask, that we have written here, check if k lies in the sorted region or not. If lies, move towards the sorted region, otherwise move in the opposite direction. So the value of k is 20. Whether the 20 element lies in the sorted region from 40 to 80, no. So what we'll do, we will move right side. We will move right side, right? We will move right side. So for moving right side, what we'll do, we will update our low pointer, low equal to mid plus 1. So the low mid value was 4, 4 plus 1, 5. So the updated low value is 5, high 8. 5 plus 8 by 2 is nothing but 13, which is nothing but 6. So now this low is updated here. This is the low, and the updated, this mid is also updated. So this is not our mid. Our mid is now this is our mid, right? Now from low to mid, is the element sorted? 90, 10. No, the element is not sorted. From mid to high, is the element sorted? 10, 20, 25. All the element which is in between mid to high, the element is sorted, right? So we can write from 6 to 8, that is from mid to high, the element is sorted. Now the next question, whether the k20 lies in the sorted region, 10, 20, 25. Yes, the k value lies in the sorted region. So we will again move towards that sorted region, that is move right side. So to move right side, what to do? We have to again update our low pointer to low equal to mid plus 1. Mid value was 6, 6 plus 1, 7. So the updated low value is 7, high is 8, 7 plus 8 by 2 is nothing but 7, right? Now again we have to change our mid pointer as well as low pointer. Low is here as well as mid is also here. Now we can see that the value that we want to search, k is equal to 20, is exactly equal to the mid, right? So we don't need to search for sorting, yes, because array of mid is equal to k. This is the element that we wanted to search, right? So at this, if this condition is satisfied, then our loop will be ended, right? And we will simply end this dry run, right? If it was not, if the element is not present, then we have to return -1, but the element is present, so we have to return the index, we have to return the mid value, right? So this was the dry run for this example, right? Now let's quickly write the code of this, right? Integer search in rotated sorted array. We have given an array, we have given the value of k that we want to search, right? Let's take two pointer, integer low is equal to 0. Let's initialize those two pointer, high is equal to n minus 1. Now again, to apply binary search, we will write the same condition, low is less than equal to high, right? We will now calculate middle value. So the formula to calculate middle value is low plus high minus low by 2. So this is the formula to calculate middle value. Now we will check if array of mid is equal to the k. So if this happens, then the element is present. So what we'll do, we will return the index of that element. So we will return simply the mid value, right? Else if array of low is less than array of mid. What does that mean? If array of low is less than array of mid, that means the element is sorted. That means from low to mid, the element is sorted. It is sorted, right? So from low to mid, the element is sorted, right? So we have to again check one condition. If the array of low element is less than equal to k and k is less than equal to array of mid, right? We are checking here whether the k lies in this sorted region or not. If the k lies in this sorted region, that means k can be there between low to mid, that we are checking. If it is there, then what we'll do, we will update our high pointer. High will be mid minus 1. Else we will update low is equal to mid plus 1, right? So this was the else if condition, right? This is the condition where else is ended, right? Else if array of low is less than array of mid, right? So this was the case. Now another case can be that, let's write one again, else. Other case can be that we are now the possibility that from mid to high it is sorted, right? So we know that if this else if low from there can be two possibility that I have shown, right? Two cases. Case one is from low to mid it is sorted. If this is the case, then we will come in this condition, else from mid to high it is sorted, right? So if from mid to high it is sorted, then we will come in this else condition, right? And again we will check for both the condition. We will check if array of mid is less than k and k is less than equal to array of high. So in that case, that means what observation can we get? That means k can be there between mid to mid plus 1 to high, right? So then what we'll do, we will move towards that, right? We will update our low is equal to mid plus 1. Else what we will do, else we will update our high pointer. High is equal to mid minus 1, and this else also loops end, right? And then if this while this is the for this line is for while, right? So this was else, this was for while loop, right? And if this condition, for this condition it does not match, this condition does not match, that means the element that we are searching is not present. So if the element is not present, we will simply return -1, right? So this was the code to search in a rotated sorted array. First we are checking if the array of mid is present in the k, then we will simply return the mid. Else if array of low is less than mid, that means from low to mid it is sorted. Then we will check the condition whether we want to go to high part or whether we want to go to low part. And if the element in the array is sorted from mid to high, then we will lies in this else condition, and again we will solve the same condition. If the array is not present, we will return -1. So this was the code. So as this is a binary search, so what is the time complexity of this code? As it is binary search, the time complexity is order of log n, and space complexity is order of 1, because for binary search we are using constant space, right? So this is how you can solve this coding question as a search in a rotated sorted array, right? So thank you for listening.